Okay. Still, we are in chapter 4, single factor experimental designs and their ANOVA. We have seen in the previous videos CRD design, the concepts of CRD. We have seen that, and also the ANOVA procedure for CRD with equal replication, and the ANOVA procedure for CRD with unequal replication. And the second design, which is important for single factor experiment, is randomized complete block design. This is the second design, and the concepts are also here. The CRD, RCBD, is what the design is one of the most widely used experimental design in field experiments or field research, and it's used for field experiments where the number of treatments is not large and the experimental area has predictable productivity gradient when there is what known source of variation. So in such case, it's we can use RCBD, and its feature is the presence of blocks in equal size, each of which contains all the treatments. The ideal source of variation to us, the basis for blocking, is one that highly and largely predictable. For example, so heterogeneity, or in a fertilizer or by trial where the yield data is character of interest, and if there is soil heterogeneity, just and if we know the source or the direction of heterogeneity, just we have to use blocking. And also when there is a direction of when there is insect migration, and when we know the direction of this insect migration in an insecticide trial, just it needs what blocking also. Whereas if there is also known source of variation in the field study of plant reactions to water stress, for example, the slope, if it has one direction, and just it needs what blocking in order to eliminate or minimize. In order to minimize the slope effect by blocking, because the blocking increases homogeneity in a block, whereas increases or maximizes heterogeneity in between blocks. After identifying the specific source of variability to be used as the basis for blocking, the size and the shape of block must be selected to maximize the variability among blocks. Here are the decisions for or guidelines for blocking. When the fertility gradient is one direction or unidirectional, just better to use long and narrow blocks, and furthermore orient the blocks so that their length is perpendicular to the direction of the gradient. If this says that if the fertility goes in the direction, blocking shall be perpendicular or need to be laid out as this one vertically. If the fertility gradient goes horizontal, yes, it needs what vertical blocking. Whereas if the fertility gradient is what's downward or the vertical direction, just blocking shall be horizontal, or the better way of the blocking direction is horizontal, and it's better to use long and narrow blocks. And the other case also when fertility gradient is two directional, with one gradient much stronger than the other, and it's better to ignore the weaker gradient, because the weaker gradient means lower variations. So we need to focus on the stronger gradient and follow the preceding guideline for the case of unidirectional gradient. That means just if we reject the weaker gradient, just better to follow this principle. The other case also, in the third case, when the vertical gradient is two directions with equal strengths and perpendicular to each other, and it's better to choose the two of the following. That means it's better. The first one is using blocks as square as possible. In this case, use long and narrow blocks with their length is perpendicular to the direction of one gradient, and use Latin square design. And when the pattern of variability is not predictable, a block should be as square as possible also. And RCBD design is used when it's very important to remove additional one source of variation due to block. So in case of CRD, it only removes the treatment differences, whereas this removes additional block of variations. That means, and also better to provide, it provides unbiased estimate of the means for the blocking categories, because there is randomization. That's why unbiased estimate of means. That means, and providing an additional information from the experiment because of blocking, an additional or extra information than that of CRD due to the presence of block. When you see the statistical model for this design, it's an additional factor or additional variable that block. That means the dependent variable is a function of population mean, treatment effect, block effect, and error effect. But in case of CRD, there was no block effect. When we see the advantages, the precision, the design is more precise, or the more precision is obtained than that of CRD, because grouping experimentally into blocks makes it to be more precise, or the information or the experiment is to be more precise. Whereas its flexibility, theoretically there is no restriction on the number of treatments and also blocks. But we know that if the number of treatments increases, replication becomes difficult, and the sources, the materials, as well as the experimental needs, the treatment materials and the experimental needs could be difficult to handle large number of treatments with its higher or large number of replications. But we can use different number of treatments and different number of replications. That's why its the flexibility is an advantage of the design. The third one is of analysis. The statistical analysis of the data is simple, not complicated, that of as compared to the other designs, that's Latin square, split plot, and the other factorial and also incomplete block designs. Rather, it doesn't compare with CRD design. When we come to the disadvantage, the missing data can cause difficulty in analysis as compared to CRD. Yeah. So, because in case of CRD, no need of estimating missing value and also biasness, whereas in case of this, there's an additional step in estimating the missing value by using missing data and also biasness, and this makes the step or the analysis difficult. And the assignment of the treatment to the units cause a problem. It's an additional work also. Just we need have to randomize the treatments to experimental units, and this is considered as also an additional problem. And also the efficiency of the design decreases as the number of treatments increases. Hence the block size increases, because if you have more number of treatments, it's difficult obtaining the homogeneous environments. That means which are categorized under the same block. That means due to this, design efficiency becomes lower, or the efficiencies becomes decreased. The main disadvantage of RCBD is that when the number of treatments large, most of the time greater than 15, the variation among the experimental is a block becomes large, resulting larger return. In such situations, other designs shall be used. When we come to the randomization in the layout of RCBD, first we have to divide the experimental into number of replications or blocks, where R is number of replication following the blocking technique. In case of RCBD, sometimes or interchangeably we can use replication instead of block, or block instead of replication, because sometimes they have similar numbers, that means even though their advantage or their purpose is different. And then after we have divided the experimental into number of blocks or replications, just we have to subdivide also each block or each replication into T number of experimental units. If we have 5 treatments, just we have to divide or subdivide the block into 5 experimental units, because of every experimental unit in the block is equivalent with the number of treatments. And then randomly allocate the treatments. Hence randomization is done with restriction, because randomization is restricted in a block, because all treatments must appear within each block, and each treatment shall be or should be assigned or randomized in only in a block. In case of CRD, all the treatments are assigned in all over the experimental units, not in a block, so not restricted in a block. In such case, randomization restricted in a block. When we come to blocking efficiency over the CRD, the primary purpose of blocking is to reduce the experimental error by eliminating the contribution of non-source of variation in experimental units, and this is done by grouping experimental into blocks such that variability within each block is minimized and variability among the block is maximized. There are two important decisions that we have to be made, that we have to make in having an appropriate and effective blocking technique. The first is the selection of the source of variability to be used as the basis for blocking. Just we have to know the direction of the source of variability, and also we have to the second one is the selection of block shape and orientation. Those points shall be considered in arriving in the decisions for appropriate and effective blocking technique. And the block efficiency. When we see the block efficiency, blocking maximizes the difference among blocks, but as small as possible difference among plots within the same block. And blocking is then based on soil heterogeneity in fertilizer and materials, and in initial body weight, age, sex, breed of an animal. That means the body weight of an animal shall be considered as a block or a group having similar or homogeneous conditions, age also, sex also, males and females and the like, and the breed of the animal is used in grouping or in blocking, and the slope of the field is also another source or another condition for blocking. During the course of the experiment, all the units in a block must be treated as uniformly as possible. For example, planting, weeding, fertilizer application, harvesting, data collection or recording operations cannot be done in one day due to some problems. Then outputs in any one block should be done at the same time. If we need to collect just a data, just every management should be finished at a time in one block. Every activity, either planting or weeding or fertilizer application, should be applied at the same day, at the same time in a block. Whereas if different individuals need to make observations of the experimental pit, then one individual should make all observations in a block. If you have five blocks and 5 different mains, those are individuals who are assigned to apply fertilizer in every block, and every individual or one individual should apply a fertilizer for all observations in a block, or for all treatments, for all experiments in a block. Similarly, all other individuals should finish similarly. And this practice helps to control variation among blocks, and thus experimental error due to variation among blocks is mathematically removed from experimental error. And first, determine the significance of replication or blocking variation by computing its values in order to see the block efficiency. So, F block efficiency is equals to F block efficiency. First, we have to see the F block, or F calculated for block is equals to mean square value of a block divided by mean square value of error. And then if the calculated value of block is larger than that of the tabular value at 1 and 5%, just the block is efficient. We can say that the block is efficient in reducing the experimental error. And to see the magnitude of reduction in experimental error, just we need to estimate the blocking relative efficiency, But in such case, just we have to use this mathematical formula, r minus 1 into mean square of the block plus r into t minus 1 into times what mean square of error, and divided by the multiplication of replication by treatment and minus 1, and times mean square of error, where the designation mean MSB is the mean square of block, whereas MSC is the mean square of error. And if the degree of freedom for RCBD is less than 20, and if our experiment degree of freedom in RCBD is less than 20, the relative efficiency of the design should be multiplied by the adjustment factor K to consider the loss in precision resulting from fewer degree of freedom. So the K, or the adjustment factor, is calculated as this one. Here it is the adjustment, the formula of adjustment factor, and this efficiency efficiency signifies that its efficiency over the use of CRD. When we compare the RCBD with CRD, the major difference between CRD and RCBD is that randomization in CRD is done without any restriction to all experimentalists, but restricted in blocks. In case of RCBD, we have seen that every treatment is randomized in every block. That means if we have 5 treatments, just each of the 5 treatments shall be randomized in one block, and additionally another randomization is applied in the next block. That means there is also an additional source of variation, that's the block in RCBD over CRD, because in case of CRD there is only 2 sources of variations, the experimental and treatment variation, and RCBD is conducted in the field experiment, whereas CRD is the laboratory or a greenhouse experimental design. These are the major differences between the 2 designs. When we come to the data tabulation, analysis, and interpretation of the results, just we can see first the analysis of variance. There are 3 sources of variation in RCBD: the block or replication, treatment, and experimental error. And there is one more source of variation over CRD because of the addition of block. And also the ANOVA will be made in the following steps. First, as we have did in the CRD, just we need to group the data by treatment, replication, and calculate the grand totals, the treatment, and replication totals. And also then we have to outline the ANOVA of RCBD. Here is the skeleton or the ANOVA of RCBD design. Here are the source of variations, 1 more over CRD, that is replication, and the other treatment, the experimental and total, are also found in the CRD, but the replication is only, or this is an additional source of variation which are found in the RCBD over CRD. Here are also the degree of freedom, R minus 1, T minus 1, and R minus 1 into and also T minus 1. Here is error degree of freedom in case of RCBD, whereas in case of CRD it was T into R minus 1, but in case of RCBD the error degree of freedom is calculated as this one. Whereas the total, when it comes to total, this is what's calculated as n minus 1. N meaning that the product of treatment by multiplied by number of replication minus 1. And also here are also the sum square values, similar fashion with that of CRD, and square values also, and calculated, and tabular values. The third step is determining the degree of freedom, as I told you this one. And whereas the next step is calculate the correction factor, that is what's squaring the grand total and divide by the product of replication and treatment. And then the fifth step is calculating sum squares for each source of variations, and also mean square values for each source of variations. So to calculate the total sum square values, just we have to square and sum all observations and subtract the correction factor. Similarly, also this one, treatment sum square values, and square all the treatment totals and divide by R, subtract correction factor, and replication sum square replaces is calculated as the summation of replication squares divided by number of treatments. This in case of treatments, just we have to use replication as denominator, and in case of replication sum squares, just treatment is used as denominator, and from such value the correction factor is subtracted, and we get each values. So after we have get the total sum square, treatment sum square, and the replication sum square values, just we can estimate also error sum square values, treatment analysis by subtracting the treatment and replication sum square values from total sum square values. And treatment mean square values also calculated as treatment SS divided by treatment degree of freedom, and replication sum mean square values calculated as replication sum square value by replication degree of freedom, whereas also error mean square values calculated as error SS over error degree of freedom. And the next step is calculating the F calculated values, or estimating F calculated values for each source of variation. For example, in this case, block and treatment. For F cal for treatment is treatment MS divided by error MS, and F calculated for block is rep MS divided by error MS. And then after we have got all these values, just we have to compare the calculated values with that tabular value independently for treatment and block, and just better to give the conclusion. But lastly, but not leastly, calculating the CV value, the coefficient of variation, and placing